Hello, we're going to continue here with our chapter on integration, and today we're going to talk about using or how to integrate trigonometric integrals. So this is not to be confused with the next section, that's trigonometric substitution. But there are certain ways that we can use to evaluate trigonometric integrals. So I'm going to break this up into three areas. We're going to talk about products of powers that involve sines and cosines, products of powers that involve tangent and secant, and then we're going to talk about just product of sines and cosines. Okay, so let's talk about powers of sines and cosines. So now we're going to have three cases here. So let's suppose that we have an integral where you're integrating the sine of x to a power times the cosine of x to another power. Now let's let m be the power of the sine function and n will be the power of the cosine function. Okay, so here's what the rule is. Case 1, if the m is odd, in other words, if the power of the sine function is odd, then we're going to write m in the form of 2k plus 1, and then we're going to use the identity for sine squared. In other words, we're going to rewrite sine of m to the x. We're going to write it as using sine squared in there, and then times sine x. Well, you'll see what I'm talking about in a minute. But once we do that, then we can replace the sine squared with 1 minus cosine squared x. So rather than cover the other cases, let me go ahead and go to this case and show you the example here for this one. Okay, so here we have, right here we have an example where the sine power is odd, and it doesn't matter what the cosine power is, but the sine power is odd. So that was case 1. So if the sine power is odd, then what we're going to do is we're going to take the sine and we're going to, since the power is the fifth, we're going to actually write this as sine to the fourth of x times sine x. So we're going to break sine to the fifth up into sine to the fourth x times sine x. And then you'll see what's going to happen next. Now, the reason we wanted this as written as sine to an even power is because now I can write sine to the fourth x as a quantity squared. So sine x to the fourth power is the same as sine x quantity squared squared. And then that allows me to use this identity up here that I told you about. So now I'm going to replace the sine squared x with 1 minus cosine squared x. So instead of sine squared x quantity squared, I have 1 minus cosine squared x quantity squared. Okay, now what we can do here is we can let u equal the cosine x, and then du would be the minus sine x dx. Now this is going to lead to, if I put a minus in here with the minus sine x, so I can just put a minus right there with the sine x, and then I can put a minus on the outside. Well, I have to put a minus on the outside if I put a minus on the inside. Well, now then this portion here, the minus sine x dx, that's actually my du. And so what I end up with, since u is cosine x, this is going to be 1 minus u squared, quantity squared, and then times another u squared. So let me show you what we end up with. So we have the minus out here, and then inside the radical we have 1 minus u squared, quantity squared, u squared. And you can square the 1 minus u squared and get 1 minus 2u squared plus u to the fourth. Then you can distribute this u squared through, and you get u squared minus 2u to the fourth plus u to the sixth. And then we know how to integrate these just using the power rule. So that would be u cubed over 3. And then u to the fourth would be u to the fifth over 5, so we'd have minus 2u to the fifth over 5. And then u to the sixth integrates to u to the seventh over 7. And then don't forget we actually had a minus in front of the integral in order to do the substitution there. And then the last step is to everywhere there's a u, go ahead and replace it with cosine. and I went ahead and distributed the minus through as well. So here I have minus the cosine cubed x over 3 plus 2 cosine to the fifth x over 5 minus cosine to the 7x over 7 plus c. And there's your answer. So that's how you deal with the first case. Now on case 1, you just had to have the power of the sine function odd. It didn't matter what the power of the cosine is. But for case 2, you have, if the power of the sine function is even, but you also have to have the power of the cosine function to be odd for this case. So let's take a look at an example of that case. Okay, so here we have sine fourth of 2x, so we have an even power for the sine function, and then cosine cubed 2x, and so we have the odd power for the cosine function. And so before we get started here, we're going to get this into the proper form so that we can get rid of this 2x. So what I'm going to do is I'm going to let theta equal 2x. So I'm going to use that substitution, and then d theta would just be 2dx. So what I would have to do then is I would have to insert a 2 with the dx. So I'd have to multiply the inside by 2 so that I have the d theta. That way the 2dx would be the d theta. And if I multiply the inside by 2, I have to multiply the outside by a half. Okay, but here's what that gives me. That gives me the form. So now I have 1/2 times the integral of sine fourth theta cosine cubed theta, because remember theta was 2x, so I can replace the 2x with theta. Okay, now this is still case 2 because the sine is an even power and the cosine is an odd power. So now we can actually rewrite this. So let's take this, and so what I'm going to do is I'm going to take the cosine cubed and I'm going to break that up using a cosine squared. So I'm going to take cosine cubed and write that as cosine squared times cosine theta. So this is similar to what I did in case 1, except this time I'm going to use the identity for cosine squared rather than the identity for sine squared. So I can replace cosine squared with 1 minus sine squared. Okay, and then what I can do there is I can let u equal sine theta, and then du would be cosine theta d theta. So that means this portion right here is just my du, and then I have in the integral, I have u to the fourth times 1 minus u squared, which I show you right here. And then of course you also have the 1/2 that's tagging along. Okay, so then distribute the u to the fourth through the 1 minus u squared, and you get u to the fourth minus u to the sixth, and then you can integrate u to the fourth and u to the sixth using the power rule. And so I get u to the fifth over 5 minus u to the seventh over 7th times a half. And so that'll be u to the fifth over 10 minus u to the 7th over 14. And then replace u with the substitution I use, sine theta. And so I get sine fifth theta over 10 minus sine seventh theta over 14. And then don't forget the constant. And then remember I substituted for theta earlier. I substituted for 2x, so theta is 2x. So let's go ahead and put it back in the original form of 2x by replacing theta with 2x. So we have sine fifth 2x over 10 minus sine to the 7th power of 2x over 14 plus a constant. And there's how you would handle the second case. Now if both powers are even, if the sine power is even and the cosine power is even, then we can actually replace, if everywhere we have a sine squared x, we can replace it with 1 minus cosine 2x over 2. And everywhere we have a cosine squared x, we replace that with 1 plus cosine 2x over 2. So we just use those identities. Okay, so let's go ahead and look at the third case. So here I have sine squared x times cosine squared x, and of course they're both even. So now I can replace sine squared x with 1 minus cosine 2x over 2, and I can replace cosine squared x with 1 plus cosine 2x over 2. And then if you multiply 1 minus cosine 2x times 1 plus cosine 2x, you actually get 1 minus cosine squared 2x. And since this denominator here it's like having 1/2 times a half, which is a fourth, I can pull the 1/4 outside. Okay, now I can break this integral up into two integrals, so I have 1/4 of dx and then minus 1/4 cosine squared of 2x. Okay, now I can use the identity again for cosine squared 2x here, so I can replace cosine squared 2x with 1 plus cosine 4x over 2, and then I went ahead and integrated this first integral. So if you integrate dx, you get x. So I got 1/4 x. And then back to the second integral, I can now break this up into, pull the 1/2 out, and I get a 1/8 because I got a fourth times a half, so that gave me the 1/8. And then I have the 1 plus cosine 4x in here. And then I can break this up into minus 1/8 dx, and then minus 1/8 times cosine 4x. And we know how to integrate cosine 4x, and we know how to integrate dx. So when I integrate the dx, I just get x. So that would be minus 1/8 x. Bring down the 1/4 x first, though, so I get 1/4 x, and then integrate the minus 1/8 integral dx, and I get minus 1/8 x. And then when you integrate cosine 4x, that would actually integrate to sine 4x over 4. And if you multiply that by 1/8, sine 4x over 4 times 1/8 would be sine 4x over 32. And of course, I had a minus in front of the integral, so it'd be minus sine 4x over 32 plus a constant. And let's see, also 1/4 x minus 1/8 x can be combined as just 1/8 x. And so the final answer is 1/8 x minus 1 over 32 sine 4x plus a constant. Now, if both m and n are odd, you can use either case 1 or case 2. Now, on this particular example, the first thing I did to get it in the proper form is I let u equal x squared, and then actually I let theta equal x squared, then d theta is 2x dx. And that would lead to sine cubed theta times cosine fifth theta d theta. And of course both exponents are odd here. So then I'm going to elect to use case 2. So I'm going to just write this as cosine fifth theta. I'm going to write that as cosine fourth theta times cosine theta. And cosine fourth theta is cosine squared theta squared. So I have cosine squared theta squared times cosine theta. Then replace the cosine squared theta with 1 minus sine squared theta. And then go ahead and freeze the video here, and you can see that I did a similar trick that I did in an earlier example where I let u equal sine theta and then du equal cosine theta d theta. And then using that substitution, then I integrated, and I replaced, when I finally got the final integral, I replaced the u with theta. And then at the very end, I had to replace the theta back with the x squared. So this is similar to a previous case. So in this example, I don't feel I need to go through every little step here, since it's very similar to a previous example that I did. So if you need to, freeze the video and then just work through the rest of it on your own here. And I also gave you a couple of practice problems down here that you can practice on and show that those integrals equal the result that I gave you here. Okay, so that ends up the case of powers of sine and cosine. And so the next one I'm going to deal with on the next video, I'll talk about products of powers of tangents and secants. So I will see you in a secant.